Alrighty, welcome. Yeah, so we are going to continue to talk about the solar wind. I've got the chat open, and please feel free to chime in verbally too, if you like. Yeah, we've been talking about the origin of the solar wind. Hold on, let me do one thing and just check my volume. Yes, okay, using the correct microphone. Yeah, we've been talking about the origin and the acceleration of the solar wind. Now I want to sort of put a capstone on that and talk about how it evolves all the way out, essentially out to into the interstellar medium. So today I really had sort of four things to talk about. One is to sort of wrap up some of the ideas that we talked about in the last few classes, the idea about the expansion of the magnetic flux tubes, determining something about whether the wind stream is fast or slow. I did see some good discussion in the chat about that. I want to, close the loop on that because some of the papers that we looked at were a bit older. So I want to talk about what's been happening lately. Then as the solar wind is evolving out through the solar system, one of the main effects that we haven't talked about yet is how the expansion interacts with the rotation of the entire system, essentially the rotation of the sun. It's locked into the magnetic field that extends out. There's a lot of co-rotating structure with the sun, and we'll talk about that. I'll say a little bit more about the turbulent fluctuations and the ongoing presence of heating in the solar wind out through the solar system also. Yeah, and then at the very end, there's the outermost structure of the heliosphere. A few weeks ago, we talked about it briefly when we looked at pictures of Murav-Over's croissant structure of the heliosphere, and I'll show you another version of that. But yeah, there's a lot of interesting transitions that happen out there. So yeah, so this first thing about the flux tubes, we've already talked a good bit about this Wang and Shealy paper, and nowadays it's generally been extended. There's the Wang-Shealy relationship between the wind speed and the expansion factor, and Nick Argy has extended that with some other parameters that I'll talk about in a second. So it's generally called the WSA model. So yeah, it's just this idea that there's this anti-correlation, and yeah, I plot several different sort of functional forms, and the original Wang-Shealy 1990 tabular ranges that I've plotted of this gray area here that sort of fall in the middle, and the actual values of wind speed that you get for certain expansion factors varies a lot because people use this model in different ways, right? Do you use it to figure out the speed at 1 AU? Do you use it to figure out the speed at the source surface and then use other ways of extending it from the source surface on out? So yeah, there are differences that way in terms of the application. But yeah, you generally see the trend there. But when you actually compare the observed solar wind with this trend, the observed solar wind is essentially a scatter plot on this diagram that doesn't necessarily follow the trend. So the original anti-correlation has been found to be improved by adding another parameter, but there's still controversy about which additional parameter works, right? Nick Argy, in the WSA model, proposed a new parameter, which is this theta angle. So it's basically, as you map the field lines back down to the sun, when you're looking at the sun, you're basically in one of these coronal holes. If you're using the PFSS definition of a coronal hole, basically the foot points of the open field. But then how close are you to the boundary of that open field region? So you can basically draw great circle angles from that point to the nearest coronal hole boundary and figure out that angle. And this figure is from Sarah McGregor's paper that tried to come up with a functional dependence of, if you know the expansion factor and you know this theta angle, what's the best way of determining the solar wind speed? Unfortunately, the solar wind doesn't sort of occupy all points in this two-dimensional diagram. Solar wind really just sort of occupies sort of one leg up here and one leg down at the bottom. So really, all the stuff in the upper right here doesn't really matter, but it's the contours of solar wind from slow to fast. So there's sort of these different regimes where it's a slow wind, the main parameter that matters is the theta. For the fast solar wind, the main parameter that matters is the expansion factor. And in between, there are these sort of bridging relationships that show how one turns into the other. And this is sort of a useful way of improving on the original Wang-Shili model. There are other suggestions, though. There's a Japanese group that proposed to use the magnitude of the magnetic field at the photosphere as this second parameter. And in fact, when they combined the magnitude with the F, that they formed this B over F ratio, and they found that pretty much that ratio is the combination of parameters that really correlates the best with the observed solar wind speed. Now, what they show here is that basically different years throughout the solar cycle have different values for this for the normalization and slope of this correlation, but it still seems to be a pretty tight correlation. So I think there are some solar wind speed forecasting methods that use this technique as well. And yeah, it's a wild west out there, and there are a lot of different ideas that people are trying. And we can try to validate these models. We can try to compare the predictions with the observations, and there are some times where it works better than others, right? So here's basically measurements of the solar wind speed at 1 AU. The data are in black and the predictions are in different colors. Sometimes something like the WSA model works great. Sometimes it doesn't. The differences between the model predictions are mostly all about differences in the telescope and the source of the magnetograms that are used to tile the solar photosphere to produce that lower boundary condition on the magnetic field that is extrapolated out to the source surface. The actual source of the magnetogram data really matters in terms of doing this. Of course, there's all these other things about what do you do when it's on the backside? How do you correct for the poles that are very poorly observed? And all these different observatories have different techniques for doing that. And again, it's still kind of a wild west where we're trying to figure out the best way to do it. I found a paper from 2014, maybe Tom has some more recent ones, that tried to do a long time comparison between the data and these models. And in general, over long times, they sort of found a correlation or a success rate of something like 50%. I think it's been kind of hard to get these models to do better than 50%. Maybe nowadays with machine learning and better corrections for the magnetograms, maybe it's doing better. But yeah, maybe when in Tom's section in a couple of weeks, we'll see some of the state of the art as to how good it can do now.
Yeah, I'll see if I can find that. This is new to me, actually, the Gressel paper. And it's surprising because MDI apparently does the worst. And that's the highest resolution kind of gold standard magnetogram among the data sets shown here.
Yeah, well, resolution and depth of accuracy of the dynamic range of the magnetogram are two independent things, and I guess there's trade-offs in the different techniques. Yeah,
it's very interesting.
I guess I only had a few other things to say about this whole flux tube topology, geometry is destiny type idea. I don't think I've actually mentioned the heliospheric current sheet very much, right? That's the place where the so-called split monopole term at the source surface, essentially where the actual split takes place, right? The dividing line between the outward and the inward magnetic fields. Essentially, it's the cusps of the large helmet streamers that exist when there's a strong north and south polar coronal hole. Sometimes when it's tilted a little bit, you can see that this current sheet or the neutral line is, undulates up and down above the equator. So basically the Earth passes through it above and below. We'll see some three-dimensional pictures of that when we talk more about rotation. But this is a very sort of classical approach to looking at the topology of the field, right? There's the one polarity, the other one with a neutral line in between. But starting about 10 years ago, there was a lot more thinking by people like Spiro Antiochus about thinking about the topological so-called separatrix surfaces of the magnetic field. Basically, when you look at the field as it's expanding out into the solar wind and you map it back down, where does it go and how does it behave? If you take a bundle of magnetic field lines way out in the solar wind, say maybe a little circle of magnetic field lines and that trace out a tube, and then you trace that down to the surface, does that tube remain a circle, or does that outline get squished or squashed or distorted because some of these field lines go in one direction and some of the neighboring field lines go in the other direction? Question about the difference between the neutral line and the current sheet. I don't know. I'm sort of treating them like synonyms. I'm sure there's a much more, I'm sure there are subtle differences between them, but right now I'm treating them as synonyms. But yeah, there are other types of features where the field lines are close together, far out, and then they diverge as you go in, but they don't necessarily have a zero of the magnetic field between them like the classical neutral line does. There are these things called pseudo streamers that have 2 or sometimes 4 magnetic loops inside. And because it's an even number, that means that if the field line is pointing out on one side, it's also pointing out on the other side. And that, when you map those down, you don't quite get a current sheet like this. So basically, when you take a map of the complex field and map it down, what these colors are showing, are something called a squashing factor, basically a way of quantifying how much distortion a circular bundle of field lines actually experiences when it's mapped down to the surface. That's the magnitude of the color from light to dark. The blue and the red are the polarities, basically the same type of polarities you're seeing here. So we do see the heliospheric current sheet mapped out between the blue and the red when we're at the source surface. Lower than the source surface, it's much more complicated because you have a lot more closed and open magnetic fields interacting with each other. But if you notice, there are these other features as well, besides, and sort of neighboring the heliospheric current sheet. These are called separatrices, or sometimes quasi-separatrix layers. There's a whole vocabulary of different terms. They basically trace out these pseudo streamers, right? So there's the same polarity on either side, but when you're right in the vicinity of it, there's a lot of squashing because, as I said, the one field line goes over here, the other field line goes over here, and there's a huge distortion. So the darker colors are the places where the huge distortion is mapped to. And Spiro Antiochus, he has a name for this. He calls it the S-web, or the separatrix-web, basically because it's a complicated web of structures that extend, 20, 30 degrees away from the heliospheric current sheet in most times. And he basically has theories of the slow formation of the slow solar wind that basically says you have to be in one of these separatrix regions to form slow solar wind, right? It's not just happening right at the current sheet, it's happening in this finite band around it. So one cool thing is to look at sort of a solar cycle's worth of these maps as the polarity flips. The magnetograms are shown at the upper left. The upper right shows the so-called coronal hole maps, right? If you map down to the photosphere, the red and the blue show the regions that eventually make it out to be positive and negative polarity solar wind. And sometimes you see red at the pole, red at the north, blue in the south, and then it flips at the other for the next 11-year solar cycle to the other polarity. And you see all these complicated separatrix surfaces, sometimes around the equator, but sometimes basically filling the entire 4π, even out at the source surface. And yeah, you can find these movies and maps at Stanford's sites. Yeah, it's kind of interesting to see how this evolves. Yeah, especially because when you're in the vicinity of these squashed field lines that get spread out as they reach the surface, these are places where you can actually encounter reconnection in the low corona that's connected up to the solar wind. There's this idea of interchange reconnection that I think we've talked about. Basically, if you have open field lines that are in the vicinity of closed field lines and you shuffle things around, you can sort of push them into each other, you can get reconnection, and bursts of reconnection can send waves and shocks up into the corona, creating variability, also create jets, and possibly even create these things that Parker Solar Probe discovered called switchbacks. As Parker Solar Probe flies through the solar wind, they find these places where the magnetic field polarity rapidly flips and then flips back. And they think that might be one of these results of interchange reconnection. So yeah, I'm just trying to knit together all these different things that we see into a semi-coherent picture, but I guess the main idea is to introduce you to all these different concepts. Yeah, the solar wind is a complicated place. Yeah, and I think we've already sort of implicitly talked about rotation, because essentially we rely on that to build these longitude, latitude synoptic magnetograms. But there's, we also realize that the corona is a low beta plasma, and if the lower boundary conditions are rotating, then the rest of that strong magnetic field region wants to also co-rotate with it, because the magnetic field sort of is in charge and the fluid is sort of lagging behind when it's low beta. So we sort of see a corona that looks like this. I think the actual colors, the actual bright colors in this movie from PSI are actually mapped by the value of that squashing factor. So we can actually see places where the magnetic field maps down to a complex region on the surface by these bright regions. All right. Yeah, I guess I wanted to talk more about how the solar wind interacts with the rotation of the sun. What we see is that, and what Parker, predicted again in 1958, was the idea of that the magnetic field forms these spiral-shaped patterns. Really, it's very similar to this so-called garden sprinkler analogy. Maybe I'll just click forward to show you the movie of the garden sprinkler. If you have a source of water that's spinning around, you could even do this yourself with a water pistol and just start spinning and have somebody above you take a look at the path of the water. If the water is pointing radially outward at every point, but you as the source of the water are rotating, the actual pattern of droplets that you see at any one time is going to form a spiral pattern. I tried to convey that in a cartoon form up here, where we have the solar wind being generated by sort of one spot on the sun, and the solar wind is at one time it produces some solar wind that accelerates out radially. That parcel keeps on moving out radially, but then at later times when the sun rotates, it produces a new parcel that goes out radially, then a new parcel that goes out radially, then a new one. And what Parker realized is that in an ideal MHD system, those points would be connected by a field line. And we'll show from MHD why that's the case in just a second. But again, it's very similar to these patterns of droplets that you can see from a rotating system. I think in fluid dynamics, I think these are called streak lines. They're not streamlines, because the individual streamlines where you follow the flow would all be radial, right? Each parcel moves out radially, but the pattern of connected features forms this spiral streak line. Yeah. If you wanted to delve into the math, we could look at MHD induction equation that tells you how the magnetic field varies in time when you have a flow through the system. I've written this as the ideal MHD version, where it's really just the one term. There's this other term that's the magnetic diffusion term, the resistivity term. But if the magnetic field is strong and the collisions are very infrequent, we have ideal MHD, where the magnetic flux is frozen to the flow. And what that means in a case like this is that as the system rotates, the magnetic field lines will be, again, tied to those parcels. So we can actually work out what it's going to look like, right? If the field is time steady, then this thing has to equal 0. We can make some other simplifying assumptions. We can assume that we're just looking in the plane of the ecliptic. So, we can use spherical coordinates. So we can assume that there's nothing entering or leaving the ecliptic. So there's no theta components. So we're just looking at the r and phi plane at theta equals pi over 2, we can also assume everything is the same everywhere around the sun, right? Axially symmetric. If you make all those assumptions, this curl of a cross product actually boils down to just a derivative of two terms. And that derivative is equal to 0 when it's all time steady. And the terms involve the radial component of the velocity, the azimuthal, forward and back along the around the rotation axis component of the velocity, and then those similar components of the magnetic field. If the derivative is 0, then this thing in the square brackets is constant, and we can estimate a value for that constant by going back down to the source surface, right? At the source surface, the field is all radial and really doesn't have any phi or azimuthal component to it. Also, the solar wind hasn't really gotten going yet, so there's really not much of a use of r down there. So really, it's just this term at the lower boundary, and we can write the rotation at the source surface really just as the rigid rotation of the sun. We can assume everything from the sun to the source surface is rotating rigidly. So the phi velocity is just the angular velocity times r. That's just assuming it's like a vinyl record where all the pieces are rotating rigidly. And if that's the constant, then we can assume that the radial field is dropping off as 1 over r squared. That's the split monopole above the source surface. We can plug that in, rearrange the algebra a little bit, and get an expression for the phi component of the magnetic field in terms of the radial component. That just involves these velocities. And when we look at the values of these, what we'll see is that these map out a spiral. This is the spiral pattern of the magnetic field. There's a cartoon of what it sort of looks like as you're going out. And one simplification that you can make is to ignore that u phi component because essentially as you're going to larger distances, the omega times r, that's growing linearly with radius, right? Again, for a vinyl record, the outer parts are moving much more fast than the inner parts. And if you go way, way out, it's whipping around very fast. So that's the dominant component. And the ratio of the b phi to br tells you the angle of the magnetic field to the radial direction. The tangent of that angle is just the ratio of those two. And yeah, this is the so-called Parker spiral angle. And if you put in values for these things, say for a typical wind speed, an average wind speed of 450 kilometers per second, and you look at different distances where this rotation velocity gets bigger and bigger as you go out, you have bigger and bigger values of this angle, and that does trace out a spiral, right? It's initially pointing radially out with a small value, and then it wraps around more tightly as you go out. It's kind of an interesting coincidence that at 1 AU, the magnitudes of B phi and BR are roughly the same. So the Parker spiral angle is roughly about 45 degrees in the minus direction. But there's a lot of other things that can vary. Like I assumed an average wind speed, but we know there's a good factor of 2 to 3 variation in the wind speed between the slow and the fast wind. And that actually makes a difference, because when we looked at that angle, it was the wind speed in the denominator. So a fast stream has a small value of the angle, so it sort of goes out more radially. The slow wind curls around and has a tighter, spiral angle. And when you have different parts of the sun, now we're sort of looking down on the North Pole of the sun at different sources of fast and slow wind at different longitudes, they can interact with each other in different ways. If the fast wind is ahead of the slow wind in the direction of the rotation, then the two wind streams are going to separate as you go out. And because the plasma is tied to the magnetic field, the plasma is going to separate, and the individual parcels of plasma are going to expand out much more rapidly than they would have otherwise. And what I drew here is the word rarefaction, right? The density is going to go down very rapidly because everything is being pulled apart much more quickly than it otherwise would have. So you can actually observe regions where the solar wind density goes way down in these rarefaction regions. Of course, what if the other combination happened? What if the slow was ahead of the fast? Then the streams actually collide with one another. And when two streams collide with one another, you get a compression, you get a density increase. This is what's called a co-rotating interaction region. And in the inner solar system, at the orbits of Mercury, Venus, and Earth, this collision is just sort of getting going for typical slow and fast streams. And you often see a bump of density at this point. By the time you get out to Mars and Jupiter, that bump actually steepens into multiple shock fronts, multiple discontinuities, because again, things just get stronger and stronger as you go further out into the solar system. The discrepancy between these slow and fast streams gets stronger. I found some other interesting cartoons of these co-rotating interaction regions. We've explored them a lot in the past few decades by flying spacecraft through them. You've got the slow wind, you've got the compression region, and the fast wind behind it. Here's an interesting plot from a space weather paper that tried to map out what are the typical things that spacecraft see as they fly through CIRs and CMEs and other types of things. And they try to, remove all the numbers and just sort of show what happens, right? So there's the slow stream, and then you see the fast stream on the other side. You see the density compression in between the two. There's also a temperature jump, and again, because the flow is tied to the field, when they compress and the density goes up, the magnitude of the magnetic field also goes up as well. Magnetic field strength is basically the density of field lines that are crammed into a certain region of space. And there's a lot of interesting other things you can observe. We'll talk more about the space weather consequences of these things passing by the Earth also in a few weeks. I've done some modeling of these things myself just by looking at the solar wind acceleration from, say, a patch of the sun. If we have a very high resolution magnetogram of a certain time, we can map those out to the plane of the ecliptic and figure out what would happen at the source surface. And then we can map that out using MHD to 1AU. And it's interesting that it turns out that in the corona, when you have high resolution magnetic maps, you can actually have very rapid transitions between fast and slow speed solar wind on small scales. If you map these different streams down to the sun, you can basically have features that are separated just by, say, a supergranule in the quiet sun here. But when you create those models and then propagate them out, you see that there's sort of a smearing effect. Essentially, as these co-rotating streams collide and separate, there's sort of a loss of information. I guess kinetic energy is being turned into thermal energy. I guess the entropy is increasing as you go out. So there really is a loss of spatial information as these stream interactions happen and you go out. Only the largest scale features survive out at 1AU. So I think when we go into, when Parker Solar Probe gets close, it's going to see much higher, much finer resolution co-rotating streams, because when you're close to the sun, there hasn't been a lot of time for those collisions and loss of information to happen yet. And also, unfortunately, that makes it hard to take what we measure at 1AU and map it back down to some location on the sun because of this loss of information. But it's a challenge. I guess I also wanted to show you these 3D pictures of, here's the different visualizations of the heliospheric current sheet and how it maps out, how it combines with the Parker spiral co-rotation, right? It's basically slow solar wind coming from the vicinity of the current sheet, fast solar wind coming from the polar regions above and below it. But when it's tilted, this region of slow solar wind resembles this undulating ballerina skirt that rotates around a given point. It's interesting. You can see the orbits of the planets in here, and a planet like the Earth goes under, then over, then under, then over, and space physics people often talk about the sector structure of the heliosphere, and that's basically these sometimes double, two unders and overs, sometimes four unders and overs. And I think I have an example of the fourfold symmetry here from the WSA Enlil model, sort of illustrating this thing. On the left, you're looking down at the plane of the ecliptic, and the green and the yellow and the red show high density compression regions. The dark blue shows the fast solar wind with the low density. And then you see different views of it, right? So in the middle, we're now looking from the side. So the plane of the ecliptic is this, x-axis here, and the north is up and the south is down. And we're sort of looking at the vertical plane that the Earth occupies. And as the structure comes out, we can see its latitudinal dependence too, right? That undulating up and down is basically passing through the undulating ballerina skirt. And then there's, you can look at the longitude versus latitude at a given radial distance, basically combining some of this information from the left, some of this information from the right, and you get them both at a given radius there as the thing co-rotates around. Yeah, kind of interesting to see how this all evolves. And these types of animations are very useful, I think, at the space weather forecasting offices, just to get a visual feel for what's heading at the Earth, which is generally this yellow dot here in the middle. Yeah, okay. One of the other things, I hate to switch gears, but one of the other things I wanted to talk about was the evolution of the heating in the solar wind, right? We talked about coronal heating. We talked about solar wind acceleration as a byproduct of the heating that was happening back in the corona. But there's a lot of evidence that the heating keeps on going, that that things like turbulence and the waves or whatever these other mechanisms of generating heat are actually keep on being important as you go out into the solar wind. And I think I showed both of these plots at various times. Sorry for them being so shrunk, but I wanted to put them both on here so that we can look at the fact that in the fast solar wind, we can measure the temperatures as they go out, from the corona all the way out into the heliosphere. And we can also measure these turbulent velocity amplitudes as they go out. So in these outermost regions, once you get almost, to 1 AU and beyond, you can sort of fit these with power laws. The temperatures are dropping off as r to the minus, 0.6 or 0.7, depending on electrons or protons. The turbulent velocity amplitudes are also dropping off like a similar power. And this is also the region where everything is expanding radially. So the density is dropping like 1 over r squared. The velocity is constant. I think these are useful to keep in mind because we can actually start to think about the balance between the heating and the cooling to try to understand those trends and try to figure out, if we can understand where they come from, right? We have our thermal energy conservation equation that we looked at back when we looked at coronal heating, right? There was we're looking at a parcel of the corona. We want to know if its thermal energy is varying in time. There's all these heating and cooling terms that determine whether energy is being dumped in or energy is being extracted out. If we just think of time steady, if we set this to 0, and we realize that when we're far out into the solar system, we really don't have to worry too much about radiation. Despite Chapman's model from the 1950s, we usually don't have to worry too much about heat conduction when we're far out into the solar system. So really, it's a balance between the heating that gets dumped in and what I call this advective term. Basically, this is the so-called adiabatic expansion term, right? If you have a parcel and it's expanding out and getting bigger, that means its density is going down. And if everything is adiabatic, that also means its temperature is going down as well. And we can look at this. We can put in these power laws for these radial derivatives. For the temperature, I'm just saying that temperature is proportional to radius to the minus some power. We don't quite know what it is, but we can actually work it out in one limit, right? If we set the heating rate to 0, then that means that the parcel really is conserving its energy as it's going out, but there's no energy being added to it. And if you work out what an adiabatic parcel must look like, going back to thermodynamics, it means its temperature goes as its density to the gamma minus 1. Gamma is this adiabatic exponent that's usually 5/3. I guess another way you could do it is just to set this equation equal to 0. And if you plug in these power laws, you can actually solve for the delta exponent. It comes out pretty straightforwardly. Either way you do it, you get that the expanding solar wind should be cooling off with a temperature dropping as R to the minus 4/3. That's the adiabatic temperature dependence. But we don't see that. 4/3 is 1.333, right? What we observed on the previous slide was 0.7, 0.6. So the adiabatic temperature drop would be much faster. We're seeing the temperature be maintained much more flatly than it would be if it was adiabatic. So what that means is that there must be continual heating, continual energy being dumped into the solar wind parcels as they're flowing out to maintain that flatter temperature gradient. And we can try to work out what all that how it should behave, right? We can use those power law dependencies of, the T is R to the minus delta, N is R to the minus 2, plug those in, and we get that when the heating rate is non-zero, that this all these things on the left give you an R to the minus 3 plus delta. So what this is saying is that just from the observations of the temperature, the heating rate should be dropping off as R to the minus 3.6 to 3.7, something like that. But we can compare that with theory. We can look at turbulence, right? We looked several times at the Kolmogorov heating rate that you get out of turbulent stirring and cascade and eventual dissipation. It goes as the density times the velocity amplitude cubed divided by some length scale, right? That's the scale over which the plasma is being stirred. There's measurements of all these things, right? There's measurements of the correlation length of the turbulence at various places in the solar system. Observations tend to show that it increases with distance from the sun by like R to the 0.5. Many simple theories just say it should increase linearly with R because this transverse scale really should sort of expand as the radius of the flux tubes as the flux tubes expand out, right? The flux tube area goes up as R squared, and the square root of that should go up as R. But in general, the more sophisticated theories give you something in between. We could plug that in. We can plug in that the density goes off as 1 over R squared. The Alfvén wave velocity amplitude, we saw it from the observations. It drops as R to the minus 0.59. There are some simple theories of Alfvén waves that often give something like R to the minus 0.5. That's if there's no damping. So the fact that it's dropping a little bit steeper than that means that the waves are damping out a little bit, which makes sense. But if you plug all that in, you get something kind of similar. It's not really the same, but you get a range of about minus 4 to minus 4.7. Yeah, okay. It doesn't overlap with what we got from just looking at the thermal dependence, but this was a very simplistic turbulence model also. There are better models that actually do a better job of matching this, but I just wanted to sort of show you the procedure of how you can use observational data to get a feel for how much heat has to be dumped in, and then use the turbulence theory to also get a feel for that. And they actually do end up comparing pretty well to one another. I guess one of the reasons why the model I just showed you doesn't work that well is that it was an isotropic turbulence model. It doesn't take into account the fact that turbulent blobs behave differently along the magnetic field versus perpendicular to the magnetic field. I think we talked about that a little bit. We talked about reconnection and MHD turbulence. There was a really nice set of observations by Craig DeForest, who actually mapped out the anisotropy of the turbulence blobs from the sun out into the, basically from the outer corona all the way into the inner solar wind. And he found that near the sun, everything was sort of stretched out radially, right? The magnetic field was very strong. Plasma beta was very low. So everything follows the field lines. But as you get further out, the plasma beta gets higher, the importance of gas pressure becomes more important. So what you tend to see further out is more isotropic structures. So Craig basically called the elongated structures near the sun striae, basically striated or field aligned, and the structures, the more isotropic, fluffy structures further out, flocculated. I think the word flocculated comes from looking at the pattern of wool on sheep because it's very fluffy and random. I think it's also been used to describe the pattern of bubbles in beer. I don't know. There's several uses of this term, but it basically means isotropically fluffy. And it's interesting that you can measure this. And there's a quick press release video on this on YouTube that you could watch as well. Oh yeah, the other thing, when you go really far out in the outer heliosphere, the temperature that was dropping much more slowly than the r to the minus 4/3 law actually stops and starts to increase. The r to the minus 0.6 or 0.7 doesn't go on forever. At around 30 astronomical units around, Neptune or Pluto, I guess, it starts to go back up again. That's kind of interesting. Chuck Smith has studied this a lot by looking at the Voyager temperature data. And what we think is happening is that the outer solar wind is starting to interact with the interstellar medium. So there are neutral atoms that sort of flow into the heliosphere, and because they're neutral, they don't feel the magnetic field, they just flow all the way in. But at some point when they're in the solar wind, they encounter a proton and they undergo this charge exchange reaction. Essentially, the neutral one gives its electron to the ionized solar wind proton, so that the solar wind proton flowing out is now neutral, and the thing that was coming in is now ionized. So then it's called a pickup ion because the ion has been picked up by this process. The velocity distributions of those pickup ions is very, very non-Maxwellian because it's not thermal. It's basically based on the velocities of stuff that was coming in from the interstellar gas. And non-Maxwellian distributions are unstable to the growth of waves. Those waves can then damp, and the damping of the waves produces this extra heating. And there's models of this that show that we can understand why this temperature starts to go up again. But yeah, I wanted to sort of continue the story all the way out to where the interstellar medium is important, and that's sort of our final topic, and that's the outermost parts of the heliosphere, right? The solar wind we've been talking about has been this sort of inner blue bubble where it's dominated by the solar wind supersonically expanding outward, but that doesn't go forever, right? There's this interstellar gas that has its own pressure that pushes back against the solar wind. And also there's this 23 kilometer per second relative flow between the sun and the material in the rest of the galaxy. It really doesn't matter whether we're thinking about the sun as the thing that's moving or the gas as the thing that's coming towards us, because it's really just a relative flow. So yeah, there are these interactions that happen. Yeah, there's a whole bunch of cartoons that show the field lines. If you've studied the Earth's magnetosphere, there's a very similar type of thing where the flow comes in, it gets decelerated and deflected, and then there's the flow coming out from the central thing, the solar wind, that also gets decelerated and deflected. And then there's this heliopause where the pressure actually balances between the two. And yeah, in addition to these cartoons, I made this for a class once just to show the different regions, right? We've got the solar wind that accelerates out and is very fast, but then it gets decelerated by this so-called termination shock, because this innermost, this middle region, the heliopause, that's the place where the decelerated solar wind and the decelerated interstellar medium gas come together, right? I think that's sort of the general place where the velocity goes to zero. And that's also the place where the pressure balances. Now, if you look at the density, there's a jump. If you look at the temperature, there's a jump. But the product between those is pretty much a constant pressure across there. So this is not a shock wave. This is a contact discontinuity. Yes, it has different values across it in terms of the density and the temperature, but the pressure is constant, and the pressure has been equalized between the two. But because the solar wind was supersonic, that supersonic flow really doesn't know about anything else happening. So that's why it has to undergo this termination shock to get decelerated to be subsonic. And a subsonic flow is sort of more easily allowed to come into this equilibrium. Same thing here. For many years, we weren't sure whether this 23 kilometers per second was supersonic out in the interstellar medium or not. So there were ideas that there would be a shock to slow it down called a bow shock. Recently, the data from the IBEX mission, I think, shows that there really isn't a bow shock. In other words, there's a pileup of gas as the material comes in, but the 23 kilometers per second is not quite supersonic compared to the local properties of the interstellar medium. So there's really only one shock and one contact discontinuity. By the way, down here in red, I overplotted that increase in the temperature due to the pickup ions, but it's really just a small thing in the grand scheme of things, because once it reaches the termination shock, it heats up a lot. All that kinetic energy that was supersonic flow gets decelerated and turned into higher entropy, right? It gets turned into hot temperature. Yeah, bow wave is what this thing is called, because it's not abrupt, but it's still something. So the pileup of gas is increasing with the age of the solar system. I don't think much of the gas is actually accreted into the inner parts, right? Most of the interstellar gas sort of gets deflected off to the side. And well, this depends on the actual shape and topology of the heliopause, right? Is the heliopause actually just this singly connected thing, or is it more complicated than that? And this is, I think, where Merav Ofer's croissant revolution has taken hold, because the outer parts of the MHD plasma depend a lot on the Parker spiral out there. Remember, of course, as you go out to larger distances, the Parker spiral angle gets bigger and bigger. It's essentially 90 degrees by the time you get out to the outer parts of the solar system. So it's basically surrounding the sun by this almost circular magnetic field. And again, a curved magnetic field exerts a tension, so-called hoop forces, which is really just tension from a circular or curved magnetic field that pulls in. So there's got to be a pressure that pushes out. And yeah, this model has sort of proposed several other forces that must be acting in a system like that go over and above what we just talked about in terms of this radial dependence. So yeah, if there's no flow, if that 23 kilometers per second was zero, it would just be this sort of collimated, almost like an astrophysical jet going at the north and south poles, because everything is B phi, and there's forces that go along it. But when there's the interstellar medium flow pushing along it, it gets deflected and turned into the croissant. Yeah, I don't think I have too much more quantitative to say about that. I think Phil Eisenberg has written some papers that tried to put this all into a context of a slightly modified, analytic model that has these features, but includes the new physics. Yeah, that is it. Yeah, I sort of wanted to give this survey of going from the acceleration of the solar wind out to the evolution all the way out to the interstellar medium. But we're sort of at the midpoint of the solar wind acceleration computation, notebook. Please keep thinking about that. And yeah, please use the Slack channel to discuss any aspect of that you might like. Yeah, I'm looking at the chat. Tom has a question for the class. How does the sun's speed through the galaxy compare to the orbital velocity of the Earth? That 23 kilometer per second is really just the relative flow between the sun's peculiar motion and the surrounding local bubble of the interstellar medium. The overall rotation of the galaxy at the point of the Earth, I think, is something like 200 kilometers per second. So everything is rotating together at that 200, but that 23 is just a slight difference between the sun and the neighboring gas. But what is the orbital velocity of the Earth? Oh, that's
So I misstated the question that I meant the ISM flow compared to the orbital velocity. And the answer is they're comparable. The orbital velocity is about 30 kilometers a second, I believe.
Is there any, I'm just wondering if that coincidence actually has an impact anywhere. I do know that the interstellar helium, not the interstellar protons that get turned into the pickup ions, but the interstellar helium that neutrals that come in are eventually sort of gravitationally focused by the sun's gravity into a point opposite the direction where they inflow. There's something called the helium focusing cone, and that actually happens around the orbit of the Earth. So there are many space missions that as the Earth orbits around and they measure that interstellar helium, they see a peak, once a year as it passes through this focusing cone.
That's good because we're running out of helium here on the Earth. So
yeah, can they bring some of it back? Yeah. Sure.
Put a big scoop up there.
Yeah, so maybe the fact that the Earth's velocity and the pattern of that focusing, maybe if the angles are of the angle of the cone is something like 45 degrees, maybe that has to do with that coincidence of orbital speed and inflow speed. I don't know.
Yeah, I was just struck by the fact that they're about the same. Those two speeds.
All righty. Well, I can stop the recording and any other chat we can have before we all go. But yeah, thanks.